सादर प्रणाम। आज़ादी के अमृत महोत्सव के अवसर पर आयोजित होने वाली एनसीईआरटी की इस वेबिनार सीरीज़ लिसनिंग टू लर्न, सुने और सीखें में आपका एक बार पुनः स्वागत है। मैं गगन गुप्ता, डिपार्टमेंट ऑफ एजुकेशन इन साइंस एंड मैथमेटिक्स एनसीईआरटी से सीआईईटी एनसीईआरटी के स्टूडियो से आप सबका स्वागत करता हूं। आज हमारा 36वां सत्र है और आज हमारे साथ स्टूडियो में हैं प्रोफेसर भानु प्रकाश सिंह, जो अलीगढ़ मुस्लिम यूनिवर्सिटी से हमारे साथ स्टूडियो में हैं। आपका स्वागत है प्रोफेसर सिंह। और आज हम बात करने वाले हैं न्यूक्लियर रेडिएशंस एंड देयर एप्लीकेशंस। न्यूक्लियर रेडिएशंस एक बहुत ही रेडिएशंस हैं जो कि न्यूक्लियस से निकलते हैं। नाभिक से निकलने वाले रेडिएशंस को न्यूक्लियर रेडिएशंस कहते हैं। ब्रॉडली कैरेक्टराइज होते हैं चार्ज पार्टिकल्स, न्यूट्रल पार्टिकल्स एंड इलेक्ट्रोमैग्नेटिक रेडिएशंस। प्रोफेसर सिंह आज हमें उन सब की रूपरेखा के बारे में बताएंगे कि किस तरह से ये रेडिएशंस निकलते हैं और उनके क्या क्या अनुप्रयोग हैं, क्या क्या एप्लीकेशंस हैं। ख़ास तौर से फूड इंडस्ट्री में न्यूक्लियर रेडिएशंस का किस तरह से उपयोग हमारे देश में हो रहा है, इन सब पर हमें विस्तार से चर्चा करेंगे। साथियों, आज का ये प्रोग्राम आप पीएम ई विद्या चैनल्स 9, 10, 11, 12 पर लाइव देख रहे हैं। साथ साथ एनसीईआरटी के यूट्यूब चैनल एनसीईआरटी ऑफिशियल पर देख रहे हैं। आप अपने प्रश्न हमें हमारे स्क्रीन पर दिखाए जा रहे ईमेल एड्रेसेस पर भी भेज सकते हैं और साथ साथ यूट्यूब चैनल के चैट बॉक्स में भी लिख सकते हैं। आप सभी का स्वागत है एक बार पुनः। डॉक्टर सिंह, मैं आपका एक बार पुनः स्वागत करता हूं। इससे पहले कि डॉक्टर सिंह अपना भाषण शुरू करें, मैं आपका परिचय प्रोफेसर सिंह के साथ कराना चाहता हूं। Dr. V.P. Singh, presently a professor of physics and chairman of the physics department, Aligarh Muslim University, was awarded a doctoral degree in experimental nuclear physics by the Aligarh Muslim University in 1991. Dr. Singh has been working on accelerator-based nuclear reaction studies with emphasis on the study of nuclear reaction dynamics of light and heavy ion-induced reactions, both at low energies. He has carried out research work at major accelerator facilities of the country like Variable Energy Cyclotron Center VECC, Kolkata, Plutonium Accelerator Facility of the Inter-University Accelerator Center IUAC, New Delhi. Dr. Singh has published about 100 research articles in international journals of repute and has also presented his research work at more than 80 conferences and symposia across India and outside. Dr. Singh has so far guided 7 doctoral theses at Aligarh Muslim University and has also successfully implemented more than 15 research projects funded by different agencies of Government of India and international agencies. Professor Bhanu has been collaborating research work with many countries like Italy, Austria, Croatia, Myanmar, Singapore, Japan, Russia, Ethiopia, France, etc. Professor Singh has also been a visiting faculty of the Yangon University, Myanmar, where he has trained their PhD students to work in experimental nuclear physics. Professor Singh has been the chairman of the Accelerator Users Committee of the Inter-University Accelerator Center IUAC, New Delhi, and has also been a member of the National Accelerator Users Committee of the Variable Energy Cyclotron Center VECC at Kolkata. Dr. Singh has co-authored 2 books entitled Fundamentals and Applications of Heavy Ion Collisions, which has been published by the Cambridge University Press, and another book, Pre-Equilibrium Emission in Statistical Nuclear Reactions, which has been published recently by the Institute of Physics, England. Professor V.P. Singh is a life member of the Indian Association of Physics Teachers, the Indian Physics Association, and member of the Indian Physical Society. He is also an alumnus of Nanyang Technological University, Singapore. Professor Bhanu Prakash Singh is also actively involved in the science popularization activities at the Aligarh Muslim University and has been associated with the Department of Science and Technologies, Government of India program called Synergistic Training Program, utilizing the scientific and technological infrastructure at different universities. So, Professor Singh, आपका स्वागत है. Viewers, you can ask your questions. We will try to take up the questions towards the end of this session at around 10:55 or so. Professor Singh, this is all yours now for next 45 minutes or so. Welcome.
Okay. Thank you very much, Dr. Gagan Gupta, for giving a quite elaborate introduction regarding myself. So thank you so much. And at the same time, I thank all the officials of the NCRT for inviting me for delivering this talk on this topic of nuclear radiations and their applications. And particularly, I'm happy to deliver this talk during the celebrations going on regarding Azadi Ka Amrit Mahotsav, which are going to culminate this year. So let me just start my talk and the presentation over here. As Dr. Gagan Gupta has already mentioned, the title of my talk will be the nuclear radiations and their applications. And हिंदी में जैसे मैं कहूँगा इसको न्यूक्लियर रेडिएशन को परमाणु विकिरण कहते हैं और एप्लीकेशन यू नो दैट इट अनुप्रयोग सो परमाणु विकिरण अनुप्रयोगों के बारे में एक संक्षिप्त प्रस्तुति प्रेजेंट करना चाहूँगा. Now, before we discuss about nuclear radiations, let me briefly tell you about that we know that all the molecules, all the material is made up of molecules, and we know that molecules are made up of atoms, and atom at the center has got a nucleus. Now, this nucleus contains neutrons and protons. This is what is already taught to all the students. Now, the protons, we know that they are positively charged particles, and neutrons are their neutral particles, and together we call them as nucleons. Now, the typical symbol of any nucleus is represented by X, where X is called chemical symbol. We have atomic mass number A, a Newton number given by N, and Z as atomic number of the nucleus. The nucleus which are inside the nucleus, that is neutrons and protons, they are bound inside the nucleus with the help of strong attractive nuclear forces. Now, the nucleus was, as we all know, that it is discovered through the famous Rutherford's large angle alpha scattering experiment, where from the large angle scattering of the alpha particles concluded, and the indication that the nucleus contains a very heavy part inside at the center of the atom, which is called as nucleus. Now, these nuclei, if I just try to plot what are the different kind of nuclei which are found in nature, and if I try to plot them on as a function of neutron number and the proton number of all stable and unstable nuclei, then I can see from here that the dotted line which is here, the black one somewhere over here, is indicating all the nuclei which are found in nature and which are all stable. At the same time, the blue points and the orange and the red point, they are indicating that these nuclei are not stable, but they are rather unstable, or they are said to be what is called radioactive nuclei. And if you plot n equal to z line, that is neutron number and proton numbers are same, then we can say that these are all having that lying on this line n equal to z. But for the stable nuclei, we find that there is a large number of neutrons as compared to that of protons. But for the lighter nuclei, we have neutron number and the proton number, both are exactly equal to same. But as the proton number increases, number of protons inside the nucleus increases, what happens is the Coulomb disruptive forces becomes important. So in order to counterbalance the Coulomb disruptive forces, a large number of neutrons are supposed to be added, or the neutrons basically counterbalances the Coulomb disruptive forces, and that's why there are a large number of neutrons as compared to that of protons inside a given nucleus. Now, the nucleus can become unstable when the energy can be added to the nucleus. For example, if a neutron is bombarded on uranium-238, then it becomes an excited nucleus, because some energy has been imparted into the uranium-238 nucleus, and we have compound system which becomes an excited. Now, this excited nucleus will try to de-excite and will come to the stable state by undergoing radioactive decay and by emitting different kinds of radiations. And these radiations can be alpha particle radiations, these can be beta particle radiations, gamma radiations, X radiations, and they can also emit neutrons. Now, when we talk about nuclear radiations, we can say that sometimes if somebody asks what is called as a radiation. Now, we can say that radiation is nothing but it is basically energy which emitted in the in the form of nuclear radiation, or rather it is energy in transit. And these radiations can be classified as non-ionizing radiations or ionizing radiations. These radiations can be in the form of a wave, or they can be in the form of particle. They can be charged particles or they can be neutral particles. So examples of neutral particles can be neutrons, they can be neutrinos. For the charged particles, we can have alpha particles, beta particles, and all that. Now, gamma radiations are also emitted in the case of nuclear radiation, in the form of nuclear radiations. These gamma radiations, we know that they are nothing but the electromagnetic radiations, and these are similar to that of light radiations, X radiation, radio wave, because they are all coming under the category of electromagnetic spectrum. The gamma radiations are emitted during the de-excitation of an excited nucleus. So an excited nucleus will emit gamma radiation, and it will de-excite by emitting gamma energy in the form of gamma radiation. One of the important properties of the gamma radiation is that they have, or rather all the electromagnetic radiations have got a speed equal to that of the speed of light. And at the same time, these gamma radiations are having high penetrating power. And if I just try to show the penetration power, I can just compare with the penetration of the alpha particles, beta particles, gamma radiations, and neutrons. Here I can say that alpha particles can be even stopped by even a thin sheet of paper. However, beta particles can be stopped by a few centimeters of plastic material. Gamma radiations, on the other hand, they can travel maybe few inches inside the lead material. And rather neutron, that's neutral particles, they can even penetrate over the large distance inside the concrete itself. So the neutrons are highly penetrating, gamma is slightly less penetrating, beta and alpha are less and lesser penetrating power. Now, the radioactive material has got an important property which we call as half-life, and half-life is nothing but it is the time required for the amount of radionuclei to reduce to half of the original value. And we have a standard equation for this, which is n equal to n naught e raised to power minus lambda t, where lambda is what is called a decay constant, and it is related to half-life of the radioactive material. Now, various radioactive material which have got different kind of half-life. I've just taken some of them just to indicate what are the typical values of half-life of the radioactive material. For example, uranium-238, which is normally found in soil, has got a half-life of 4.5 billion years. So it is much longer half-life. Potassium-40, which is found in soil, and even the potassium-40 is found inside the human body, and also sometimes it is found in the concrete material, in the bricks and all that. It has got a half-life of 1.3 billion years. Similarly, the carbon-14, which is found in all living tissues, has got a half-life of 5,730 years. Hydrogen-3, which is nothing but tritium, which is found in all waters, has got a half-life of 12 years or so. On the other hand, half-lives of different materials are also small. Iodine-131 has got half-life of 8 days. Technetium-99m, metastable state, has got a half-life of 6 hours. Gold-198, which is generally used in tumor therapy, has got a half-life of 2.7 days. And even half-life of different materials can be lesser and lesser. So half-life, I can see that they can vary from billions of years to a few days or few hours or few seconds as well. Now, depending on the values of this half-life, they have got different kind of applications in various fields, and they can be used for various societal benefits. The typical sources of these radiations I can just mention over here is that there can be two different kinds of sources. There can be natural sources or there can be man-made sources. In natural sources, I can say that nuclear radiations are produced in the cosmic radiation. They come in the form of cosmic radiation. They are coming from the sunlight in the form of sunlight as well. The radon, which is also a radioactive gas, they are produced from there. Then living things also can be said to be the sources of natural radiation. Then soils and rocks, they also emit various kinds of nuclear radiation. Regarding man-made sources, I can say that weapon fallout, we know that it is one of the source of nuclear radiation. Then medical and dental X-rays, we undergo X-ray of different parts of the body, or the dental X-ray. Then the X-ray machines are also the source of radiation. Then even the nuclear reactors, nuclear power plant, the coal power plant, from there also, somebody can say that in the coal power plant there is no nuclear radiation. But inside the coal also there are a small amount of some the radioactive elements which are present. So nuclear power plant as well as thermal power plant or the coal power plant also produce a small amount of radiation. Then there are smoke detectors, from where radiation is emitted, then various industrial applications, they use radioactive material, so they can be source of radiation. Then in research, we use different kind of radioactive sources in the universities, in the different kind of laboratories. So various kind of radioactive sources are used, and we have these sources can be said to be some of the man-made sources. The radiations can be used for human welfare in the field, various kind of fields. Some of the fields I have just noted over here. One of the fields can be in the field of medical diagnostic and treatment. The nuclear radiations have been used successfully for the diagnostic as well as for treatment. At the same time, there are various research applications. Nuclear radiations can be used for industrial and manufacturing applications. Then nuclear reactors, we know that if it is one of the important place where the nuclear energy is generated with the help of nuclear reactors, then electric power is generated with the help of nuclear reactors, then nuclear radiations are used for space power, spacecraft power supply, and they are also used in consumer products, safety and security. I will just elaborate some of them over here. Then nuclear radiations are also used for food irradiation in order to have security of food and safety and preservation of foods. Like in medical uses, I can say, I already mentioned that there can be a diagnostic use and there can be therapeutic use. In diagnostic, I can say that generally low doses of radiations are imparted for the diagnostic, and the short time exposures are used. For example, we go for X-rays of different parts of the body. If there is some fracture in the bone, then we go for the X-ray, and then there we say that we know that the short time exposure is given. Then for therapeutic, I can say that for the treatment purposes, generally high doses of radiations are given, and in that case, there are generally long time exposure are given to the human body. So diagnostic uses can be X-ray radiations where we have short exposures. So in terms of radiographs, fluoroscopy, CT scan, dental X-ray, chest X-rays, mammograms. Then in case of therapeutic, we have nuclear medicines which can be used for the treatment of various kind of diseases. Medical uses, again I can say that in case of medical uses in nuclear medicine, we know that a suitable radioactive material is injected inside the body of the patient. And these material which is injected inside the human body, they emit gamma radiations and they are detected in order to get an image with the help of computer analysis. So they are used in this case for the locating tumors inside the body and also at the same time for determining functions of the organ inside the body. We know that a CT scan is very popular, which is taken with the help of X-ray radiations. So we know that full form of the CT scanner thing, it is computerized tomography, which combines a series of X-ray images taken from different angles around the body and uses the computer processing to give the cross-sectional images of the bones, blood vessels, the soft tissues inside the body. And it helps to provide more detailed information as compared to normal X-rays which are done. So it is well suited for quickly examining the people having internal injuries from the accident. Sometimes we know that there is some accident on the road, so there is some head injury, we rush to the patient for undergoing CT scan. From there it is possible to find out various diagnostic purposes. Then one of the other application can be fluoroscopy, where fluoroscopy is nothing, it is a kind of medical procedure that makes a real-time video of the movement which takes place inside the parts of body by passing the X-rays through the body over a period of time. But in this case, what happens is the time of exposure is a little longer, maybe from minutes to maybe a few tens of minutes can be there. So in that case, some high doses are imparted or high dose of radiation is imparted to the human body. Then there is another important radioisotope which is generally used for the medical diagnostic is that of what is called as technetium-99. And this M I have indicated here indicating that the 99 technetium is in metastable state. Now I can also mention here is that technetium, the name technetium is given because of the fact that technetium is, it is given the name because it is technically produced, meaning thereby it is not found in nature, but it is produced artificially with the help of nuclear reactions. So 99 technetium metastable state is used as a radioactive tracer in almost like over 80% of all nuclear magnetic diagnostic procedures. An important thing about this technetium-99 metastability is that it has got a half-life of only about 6 hours, and this 6 hours half-life is very important, and it is sufficient enough to determine the various physiological processes, and also it is quite long enough so that it dies out because it has got half-life of 6 hours. So in like almost like within 24 hours or so, 93% of the radioactive material will decay out from the body, and as within 24 hours the exposure will become quite low. So it is used in a large number of medical diagnostic procedures, and it in large number of large number of diagnostic procedures, and at the same time I will say that it is well suited for this kind of diagnostic roles because it emits gamma radiations of only 140 keV, and 140 keV means that it is a low energy radiation, and it can be easily detected by the gamma cameras because the gamma cameras has got better efficiencies at low energies, and if the energy of the gamma radiation is large enough, then efficiency of the detectors becomes small. So at low energy, efficiency of the detectors are large, and hence they can be easily detected, and we get better image with the help of low energy gamma radiations. Now, so this 99 technetium scans have been used to detect a wide range of conditions including injuries, infections, tumors, heart disease, thyroid function, kidney conditions, and also it is also used to guide some cancer procedures as well. And this 99 technetium can be administered into the human body with the help of intravenous injections, or it can be also sometimes given orally. Now, on the other hand, other kind of radiations which we have, the charged particle radiations. For the charged particle radiations, we know that for the charged particles and the gamma radiation, they interact with the material or with any body in different ways. The charged particle loses energy by the process of ionization and excitation, and this is a famous expression which is called as Bethe-Bloch formula, dE by dx, or it is energy loss per unit path length. And we know that this energy loss per unit path length depends on velocity of the particle. It also depends on what the charge of the incident particle is small z. And also at the same time it is depending on velocity square, or rather I can say that it is depending inversely on the energy of the incident charge particle. So the d by dx, or the energy loss per unit path length, basically changes, decreases as a function of energy, like almost like exponentially, and we can see that if the energy of the incident charge particle is low, then there is a large energy loss per unit path length, but for high energy charged particles we know that energy loss per unit path length will become smaller and smaller. Now this property has been beautifully converted and can be converted in the form of Bragg curve. The Bragg curve means that if we plot d by dx, or when the particle of a given energy E enters inside the medium, then it loses energy. Initially it has got large energy, but as it enters in the medium, it loses energy and its energy becomes smaller. When energy becomes smaller, then energy loss per unit path length goes on changing in such a way that we have large d by dx, or large energy loss per unit path length at smaller energies. As we can see from here, there is a large d by dx, or energy loss per unit path length at smaller energies, and then there is a large amount of ionization at lower energies. So for a single particle we can have this kind of curve, but when we have a beam of particles, parallel beam of particles, we have almost like a modified curve, which is the dotted curve which is shown over here, and this curve is popularly called as a Bragg curve. And if in this right hand side curve I plotted a specific ionization for 7.69 MeV alpha particles which are emitted from 214 polonium. Now important thing over here is, we can see from this figure or this figure, we can say that maximum amount of energy lost towards the end of the range. So maximum energy is lost towards the end of the range when the particle reaches toward the end of the range, or when it is going to stop over here. And this property is basically compared for different kind of particles. Like for charged particles, we have this red curve over here, and with the help of red curve, for example, for 200 MeV protons, we have the red curve here. We can see that there is maximum energy loss per unit path length, or maximum energy lost toward the end of the range. But if we compare it for the gamma radiations, like this magenta curve, purple curve, the green curve, or the X-rays, we see that most of the energy deposited in the front part of the surface over here. But the charged particle loses energy towards the end of the range. That means if you are interested in depositing a large amount of energy at a certain amount of depth, then we can say that charged particles are better suited. And in that regard, because of this Bragg curve property, the charged particles are useful in various kind of therapy, cancer therapy, and we have a popular therapy which is called as proton therapy. And here important thing is the penetration depth can be well defined and it can be adjustable by suitably choosing the energy within the charged particle, and most of the energy will get deposited at the end of the range, and no dose will be beyond this range, this target. So if the target is somewhere here, so we have minimal amount of dose which is administered on the front portion. The dose to the normal tissue in this case can be minimized, and hence it has got a property of good tumor kill. So that's why proton therapy has become very, very popular throughout the world for the case of the treatment of the cancer. The protons basically enables delivery of high dose to the tumor, sparing the surrounding tissue. So these tissues and the front surface, they can be spared up. However, inside the body at a certain depth, we can deliver more amount of energy, and the tissues can be damaged with the help of this, and hence we can speed up the treatment program for any person. So there are various machines throughout the world which are being used for the proton beam therapy. So this is one of the machines like cyclotron for proton therapy, and almost in several hospitals, even in India, we have linear accelerators where the proton beam therapy is being used, and so many patients are getting benefit out of that. Now there are several applications in the field of manufacturing industries. For example, in the field of testing and measurements, nuclear radiations are used for monitoring the thickness of the material, or for materials which are due to the production at the same time. Then it is possible to measure the thickness of the sheet of metals, aluminum foils, which we generally use in our maybe in the kitchen also as well. With the thickness of the aluminum foils can be monitored with the help of nuclear radiation. The thickness of the new paper sheet can also be measured, can be determined, and then measuring the wear or the wear and tear on the cutting and the drilling tools is also possible. And there are various other measurements like the glue, how much glue has been put on the postage stamp, level of liquid in the canned beverage. This is also possible to measure and is being used all the way. So coming back to application in industry, we have well logging. Radiations are being used, density, they're used as density gauges, we can determine density of the materials. Then also they are being used for sterilization of various kind of equipment like medical instruments, cosmetics. So earlier we used to sterilize our medical instruments by just boiling them in the hot water. But now the nuclear radiations used for treating them for the sterilization. Then cosmetics are also sterilized by using the nuclear radiation. Then foods and spices, they're all getting sterilized. So they have got a variety of application in the field of industries as well. As I mentioned about the thickness of material, then normally an student, when you are in 6th or 7th or 8th class, you know that thickness is measured by using a vernier calipers, or you measure the thickness with the help of screw gauge. But the screw gauge or vernier caliper, they have got a limitation. The vernier calipers can have a least count of something like 0.01 millimeter. Screw gauge 0.001 millimeter. But if the thickness of the sample is much smaller, then it is difficult to measure the thickness with the help of these two kind of machines. Therefore, nuclear radiation comes for our help. For example, one of the techniques is what is called alpha transmission technique, which is used for thickness measurement. And most of the time, this alpha transmission technique is being used in the research purposes when any experimentalist is going to conduct an experiment. So knowing the thickness of the sample is very, very important in any experiment. Therefore, in order to measure the thickness, I need to have a very precise measurement thickness required. And for that, we take an alpha particle source of a known energy, and the alpha particles are emitted from the source. So we record the spectrum, we measure the energy without the sample and with the sample, and with that case, what happens is if I say that this is without any energy loss, and when we put the sample we have energy loss, so we can measure how much energy loss is there. So energy loss can be measured, so I can measure what is the amount of delta E, that energy loss when this in radiation or the alpha particle radiation emitted from 241 emission, they pass through the given file. And once I know that energy loss per path length, it is possible to measure thickness of the material. So in this case, for example, when the students have given me the slide, and I can see that one sample of aluminum has got a thickness of 70 microgram per centimeter square, which is much smaller and cannot be measured with the help of simple the screw gauge or the vernier calipers. Nuclear radiations are also being used for nuclear level measurements. For that, we generally take a source of cesium or the cobalt-60 is taken, and we have nuclear radiation coming out from here. And then in this bottle, for example, we have a liquid. Without the liquid, we have a number of radiations which are detected by the detector. But as soon as the level gets down filling, radiation reaching to the detector gets stopped. And in this way, we can know that whether our vessel is getting filled or not. So in this way, it is possible to determine the level measurement is being done. And it is very popular for measuring the level of beverages in the can and with different cans and boxes and all that. And coming back to that of applications in research, I can say that there are a variety of biological and genetic research applications in the field of agriculture research, applications in the field of space research, pharmaceutical research, and then various basic sciences we have applications. Now, what is the basic mechanism when we come to that of biological research? So, what happens is when the radiation enters in the material, it gives rise to some kind of biological damage. The basic mechanism of the biological damage is that they are again categorized into two categories as direct effect and there can be indirect effect. Radiation itself interacts with the cellular protein or DNA, altering the chemical property of the molecule, and in case of indirect effect, radiation interacts with the water inside the body to create free radicals which then will attack other cell molecules and all that. I can also mention that there are certain myths about the nuclear radiation. But one of the important myths is, one of the popular myths is that we have to stay away from irradiated food because it is radioactive and it is dangerous. But the fact is, the irradiation or the radiation when bombarded to the food in proper amount kills bacteria that makes you sick. So it does not make the food radioactive or does not make the food harmful, or there are no harmful chemicals getting into the material. It is also said that there is no safe dose of radiation, but I can say that there is a safe dose of radiation if a certain amount of radiation coming out, because in our atmosphere also there are large amount of radiations which are naturally occurring in the medium. The plutonium-238 is also one of the important kind of radioactive material which is being used for various kind of applications. It emits alpha particles of about 5.593 MeV, and it basically generates significant amount of heat through its radioactive decay process, which makes it useful as a heat source for sensitive electrical components in a satellite, for example, as well as a power source in various kind of batteries which are used in satellite. Half-life of this proton-238 is 87.7 years, and hence it makes it very suitable for a long time battery source applications. The plutonium batteries are also useful for what is called a pacemakers, because they have got very long half-life, and it has been successfully used as one of the power source for the pacemakers that have been used. So over the years, the various kind of power sources have been used for pacemakers, including the radioactive materials which are used as plutonium-238 in case of pacemakers. Now, important thing is that due to the extremely long battery half-life, the nuclear pacemakers tended to outlive their users and could not be bred with them due to radiation exposure risk. Therefore, it has to be taken out at the time of death of any person. It is being used in a spacecraft power supply. small electric sources have been provided the heat to the electrical power for space applications for since a long time. Safety and security of the consumer products is also important. We have the smoke detection equipment, self-powered lighting or the exit signs, lighted aircraft instrumentation, pharmaceutical detection, bomb weapon detection, scanning and surveillance equipment, theft detection systems also be using nuclear radiation. Then the food irradiation is very important component where the nuclear radiations are being used successfully. But I can just mention why the food irradiation. I can answer that. The answer to this is for the food safety, because the fact that almost 1 in 10 people in the world fall ill after eating contaminated food, and almost 420,000 die every year, resulting in the loss of more than 30 million healthy life years. And children under the age of 5 years carry about 40% of the foodborne diseases, and with 125,000 deaths every year. So foodborne diseases basically impede socio-economic development by straining healthcare systems and harming the national economic sources, tourism, trade and all that. And more than 76 billion illnesses are coming because of food, this kind of food which people are eating. More than 325,000 hospitalization, more than 5,000 of deaths. So there is a lot of problems with the food which is not proper or it is not safe. Now approximately 25% of the worldwide food production is lost after harvesting due to insects, bacteria and spoilage. So there is economic losses globally. So this equates to about like food losses, their waste accounts up to like 10% of the greenhouse emission. They use up precious land for water resources at the same time for essentially nothing. So I can say that food irradiation is nothing but it is one process and has got multiple uses. We can inhibit the sprouting of the material, sprouting of the onions, potato, ginger, garlic. The insect disinfection can be done for cereals, pulses, dry fruits, shelf-life extension of various chicken, meat, fish, then pathogen reduction in spices, flesh, food, then the fruits can also be quarantined and making the lifetime of the shelf life of the food can be increased, fruits can be increased. The end benefit of the food irradiation will become that there will be decreased incidence of foodborne diseases, reduced spoilage of global food supply, increased level of quality assurances in the internal market. Access to sufficient amount of safe and nutritious food is basically the key to sustaining life and promoting good health of our society. Again, I have already mentioned that the various popular things which can be irradiated, like medical devices, are irradiated with the help of nuclear radiation, the wine corks, food packaging, cosmetics, ingredients, and all that. How does food irradiation basically help? When the food is exposed to carefully controlled amount of radiation, it decreases the disease-causing germs, which become lesser in number. Bacteria which causes spoiling are reduced, and sprouting is becomes slow, or it is almost sometimes stopped in some cases. And if you are scared with this irradiated food, or you are worried about the irradiated food, then we can say that the most of the food is made up of dead cells, and DNA damages to the food because of irradiation is irrelevant in that case. So this myth can be resolved. Remaining the living cells causes sprouting and spoilage, and when we irradiate the food, the DNA damage delays sprouting and it prevents sprouting. So there are so many applications where we can say that we should not be scared of the irradiated food because of all these myths. The strawberries, we know the strawberries have got a very short shelf life, but if you have non-irradiated the strawberries kept after 15 days, and these are on the right side you have irradiated after 15 days, and we can see that on the right hand side the strawberries are well proper in shape and they can be eaten up and not giving rise to any kind of problem. And on the left hand side we can say that they're almost spoiled over here. So these are one of the applications where we can see that we can increase the shelf life of the strawberries. Now sometimes some people can say that irradiation changes the makeup of the food, and as an expert we can say that yes, it changes the makeup of the food, but other food processing methods, they also do the same thing. What it means, when we heat food, it causes some changes. By heating the food, there are some kind of changes which are taking place in the food, but at the same time when you microwave the food, it also causes a change, and when you fry the food, it also causes the changes. So whenever you do any processing, there will be some change. But what happens to the food when it is irradiated is not very much different. Only thing is you have to irradiate the food with a controlled amount of radiation, and then our food will be much safer. Whenever we are going to purchase any food which is irradiated, this kind of symbol which is there on the right hand side, the green, is called a radura. As per the government guidelines, this symbol has to be put over there, and there should be indication that the food is basically irradiated food. There are several facilities for food irradiation. So this is one of the pictures of the facility for food irradiation, where the food is put inside the facility and after irradiation it is taken out. So this is a typical carrier irradiator, which is a typical kind of facility. Now facility accident and waste, sometimes we can say that there may be some accidents or there will be some waste which are coming out. So answer to this can be the severe accidents are not possible. Electron beams and X-ray sources which are used for irradiation can be easily turned off and easily can be stopped. Gamma ray sources cannot automatically blow up, they will not become like a bomb, and the facilities itself cannot become radioactive, and hence almost there is no radioactive waste which is getting produced. And these cobalt-60 gamma radiation sources which are generally used, that they can be recycled, they can be regenerated, and hence we can say that they're all facilities are safe and almost no radioactive waste is produced. So not only one or two, but there are a large number of radiation processing facilities in the country, even in our country, which are being run in the country for the food processing in India. I've just given a small list of these factories or the industry where the food irradiation is being going on, and people are getting benefited with this. This is a long list. So some of the main sources of food irradiation, as I mentioned, that they can be electron beam, there can be X-ray radiations, there can be gamma radiations. In case of electron radiation, we know that the students know that the beam of electrons is accelerated by an electron gun, similar to the beam of electrons which comes in the cathode tube of or the TV tube, and it can be turned on or off since it uses no radioactive material. So electron can come out without any radioactive material itself. Electron beam can also penetrate about maybe 1 or 2 inches inside the given material. So advantage is it does not require very thick walls, containment pool or disposal radioactive waste material is not done in case of when we are using electron beam as one of the radiation facilities. However, for gamma radiations are successfully being used since last more than 40 or 50 years for sterilization of medical, dental, household products and medical equipments. So gamma rays can penetrate the food to a set depth of maybe several feet, so they are much better as compared to the X-rays. Now gamma rays, as I had already mentioned, that emitted from the spontaneous radioactive decay. So we can have a pencil of the cobalt-60 material which emit gamma rays of 1.17 and 1.33 MeV gamma radiation, and they can be easily turned off or turned on by lowering the cobalt source into the storage pools, and they can be taken out so that radiation can come out. And now, according to the Department of Atomic Energy, Government of India, the gamma radiation is the answer to the problems of producers and exporters of the spices. Now, since the gamma rays have high penetrating power, spices can be irradiated even after packaging the spices in the packet, And irrespective of the size of the carton, we can be small size or we can be big size, gamma radiation can penetrate maybe even few feet inside the carton. So it ensures that there is no contamination at the time of opening of the package. So gamma radiation are not the charged particles, so they will not contaminate the spices and all that. The cost of food irradiation is also there. Whenever we are irradiating food, there will be some cost involved in that. So like any other food process, irradiation will also add to the cost of the food. Initially, something like 2 to 3 pounds euro per pound for producing 3 to 5 pounds. So for beef, for there some a list. So I just want to mention that it will definitely add to some cost of irradiation, but similar to that of other methods of preserving food. Now, safety of irradiation facility is important. Here it can be mentioned that there is no exposure of radiation is done to the public with the help of these kind of facilities, and there are independent regulators governed by the Department of Energy and the government, where it is successfully getting monitored that there is no exposure of radiation and there is no other kind of problems with the machine. The food irradiation is basically a part of comprehensive food safety. Food irradiation is not a replacement for the comprehensive food safety. In fact, the food irradiation cannot reverse the food spoilage process, but irradiated food need to be stored, handled and cooked in the similar way in the normal way. So it will not reverse the food spoilage, but it can improve the shelf life of the food, can be improved with the help of irradiation. So there are many countries which have approved the food irradiation. The long list of countries have been given, and APIDA in India, Agriculture Processed Food Control System Development Authority, it is taking care of these kind of approval of food irradiation facilities in the country. And now there is a word of caution. If you use very large doses of radiation and much larger than what is required, you can make the food radioactive. But it would be just like putting something in the microwave oven for a long time, and you know that when you put something in the microwave oven, it will catch fire. So similarly, when you are radiating a food with a radioactive material, then it will also become bad. At the small levels of radiation, which are generally used to irradiate food, we can definitely say that there is no possibility of food becoming radioactive. Now, end results are that there are a variety of benefits of food irradiation. Sometimes the people are taking the raw egg, they mix the raw egg in the milk and they drink it. But this raw egg may have some kind of different kind of bacteria. But if you irradiate it with some kind of gamma radiation, then it can become non-infectious. So disease-causing germs can be reduced, or they can be almost eliminated with the help of irradiation by gamma radiations or electron radiation. Nutritional value of the food is also preserved without any problem. I have not listed over here, but we can say that when we compare nutritional value of the food which is irradiated or which is not irradiated, it has been found that the nutrition value of the food is almost like preserved. It leads to decreased incidences of food-borne illnesses. So when our food is well preserved, then there will definitely, it is going to lead to the food-borne diseases will become lesser and lesser. And at the same time, a spoilage of the global food supply will also get reduced because you are preserving the food for a long time, and hence it will increase the level of quality of assurance in international trade of the food products. So these are some of the pictures. On the left hand side I can show that these are all irradiated foods, and we can see that even after a few days or several days, they looks almost like fresh and they are not getting destroyed or spoiled. With this, I would like to just end up, and I would thank you all, saying that the food irradiation means safer food, and only thing is that we need to get aware about these kind of facilities which are available and how we can get benefited of nuclear radiations for our society and for the societal benefit. Thank you so much for your kind attention. Thank you.
So thank you, Dr. Singh. Excellent talk, excellent exposure to the uses of nuclear radiations in different fields, and particularly in the areas of the food industries at all. There are many questions which we are receiving. Let me start directly right from the, try to be in chronology of the talk which you have delivered. You talked about the uranium-238 in the beginning. The half-life you mentioned around 4.5 billion years ago, लगभग 4,500 करोड़ साल, 4.5 अरब साल, और लगभग यही उम्र है हमारी धरती की। तो प्रश्न ये है कि हमें कैसे मालूम पड़ा, किस तरह से हमने उसकी हाफ लाइफ को मेजर किया कि जो कि हम इस पर्टिकुलर नंबर, अराउंड इस नंबर पर पहुंच सकें। कुछ
ऐसा है कि हाफ लाइफ मेजर करने के बहुत से तरीके हैं। ये डिपेंड करता है कि हम किस मटेरियल के हाफ लाइफ को मेजर करना चाहते हैं। ये देखना होता है कि उसमें किस तरह के रेडिएशन एमिट हो रहे हैं। तो वी जनरली मेजर the amount of radiations at a given time. Half-life we define anything, but it is the amount of the material which becomes half of the initial value. Okay, so activity of the sample becomes half of the initial value, and we can definitely determine it. So there are methods for determining when if the sample is emitting alpha particles, then we measure the number of alpha particles at different time intervals. Or there are other techniques like recent techniques are nothing but they call accelerated mass spectroscopy technique, where it has become possible to even a small amount of material which has got a long half-life can be detected with the help of accelerator-based mass spectroscopy systems. So there are many techniques which are used. So
basically, if you take a large sample, for example, a large sample of any radioactive material, and you see that how it is disintegrating with time, no matter whether it has really been deteriorated to half of its value or so, and that can be done through the techniques which you just mentioned, X-mass, etc. Yes, so coming related to it, which is slightly away from what you delivered to us today, the same technique can be used to identify the ages.
Yeah,
the dating mechanisms.
Definitely.
The carbon dating has got its own merits, has got its own demerits, limitations, not demerits, I am sorry to use the word, has got its own limitations. We know the uranium dating, there are nearly 15 or a half or a dozen kind of deuterium, these dating mechanisms. So can we use this uranium uranium or nuclear dating mechanisms, particularly in the backdrop of this question is this which we are receiving from the children and other persons, those who have joined us through different media. Yes, if you want to see that, suppose if there is an idol which was created say nearly 10,000 years ago or 1,000 years ago, if you see the carbon dating, if you made an experiment of carbon dating or uranium dating into that, you will find the age of the stone, that is millions of years. So is there any mechanism that you can find that when it was cut, when it was polished, or when it was processed? The
recent technique is nothing but this is what I mentioned, that accelerated mass spectroscopy. And I will just like mention over here is that this accelerated mass spectroscopy technique is basically being used nowadays even in our country. At IUAC center they have a EMS facility there. And this
atomic mass spectroscopy.
Accelerated mass, not atomic. Okay. It is called accelerated mass spectroscopy. Even if a very small amount of material, that can be counted with the help of your accelerator mass spectroscopy technique. So carbon-14 dating was a quite long and obsolete kind of thing, I will say. Now with the help of accelerator mass spectroscopy, it has become much easier and easier to get this dating process being done. So,
so what kind of radioisotopes which you use in this?
There is the carbon-14 can be detected there, aluminum-27 can be detected, maybe some isotope magnesium, and heavy elements can also be detected.
That's
so
great.
there are worldwide there are dedicated machines for different kind of isotopes getting separated, and on the basis of that they determine the half-life of the material.
Half-life of the material. That's great. And then Yes, so almost everything can be
almost
everything can be found.
There are machines, there are accelerator machines in Sweden, so they're doing variety of measurements are being done for.
अच्छा, ये हमारे देश में ये जैसे आपने पेलेट्रॉन एक्सीलरेटर सेंटर बताया, एक कलकत्ता का है, एक यहाँ का है और दिल्ली में है, इसके अलावा भी कुछ और जगहों पर कुछ है हमारे देश में?
एक्सेलरेटर सेंटर्स तो कई हैं हमारी कंट्री में जो है,
पेलेट्रॉन
और पेलेट्रॉन टाटा इंस्टीट्यूट ऑफ फंडामेंटल रिसर्च बॉम्बे में है, एक इंटरयूनिवर्सिटी एक्सेलरेटर सेंटर अभी जेएनयू कैंपस के पास में है सेंटर, वहाँ पे पेलेट्रॉन एक्सेलरेटर है, एक साइक्लोट्रॉन मशीन है, वेरिएबल एनर्जी साइक्लोट्रॉन सेंटर कोलकाता इंडिया में है। और यहाँ मैं एक चीज़ ऐड करना चाहूँगा, क्योंकि मैं अलीगढ़ से आया हूँ, तो यहाँ ये ऐड करना चाहूँगा कि वन ऑफ द फर्स्ट न्यूट्रॉन जनरेटर मशीन वाज in-house built at the physics department of Aligarh University, and you must be remembering.
Yes, we remember.
So it was the first machine which was built at the Aligarh University physics department.
Yes, that's great. Yes, I remember that. I hope that particular machine may be kept as a maybe brought again to the operating situations and then can be put or can be managed for demonstration point of view, and maybe some small masters level experiments can still be performed for doing it. After all, we have GM counters, scintillation counters, etc. in our masters or undergraduate level programs.
Definitely.
Yes, another, there are many questions with us. I am taking one by one. So another important question which appeared to me is that why do we use X-rays? Yes, friends, before I go to Professor Singh for this question, the soft X-rays are used. Yes, and why do we use X-rays for in X-rays or in CTs? The basic reason is that we have water windows. Water windows means that the reason where the rays find water to be transparent. So they can penetrate through these waters. Yes, the X-rays machines which are the CT machines which they use X-rays are of the order of 4.40 nanometers to 2.33 nanometers wavelength. And these radiations or the X-ray radiations are basically coming from carbon, I believe, carbon source, and nowadays they are being replaced by technetium.
X-rays are used from they are not coming from technetium. Technetium gives you gamma.
Now this technetium gives you gamma. Yes, many CT machines are using gamma radiations, as you mentioned too. So what happens? This becomes very easy to find out, friends, to detect or to analyze or to diagnose the samples in while they are in the body in vitro. Whatsoever we call in vitro situation, we need not to preserve them, we need not to take them out and perform in vivo experiment with them. I think that I had given that answer to that why do we use X-rays. And now coming back to this, that how these are different from gamma ray sources, why can't we use the same carbon sources? And
X-rays and gamma rays, as maybe all the students know, that basically both of them are electromagnetic in nature. They have the part of the electromagnetic spectrum. The basic difference in terms of their energies. X-rays have got smaller energies as compared to that of gamma rays. The basic difference between is that in terms of the origin of these X-rays and gamma rays. And you know that X-rays are originated from the atomic de-excitation. However, gamma radiation originates from nuclear de-excitation. When the nucleus de-excites, it emits gamma radiation, and the nuclear energy levels are having a large energy, so therefore the radiations are having larger energy, but atomic de-excitation, or I can say that atomic levels are closely spaced, and hence the energy will be lesser. So typically the X-rays have energy of the order of maybe
few hundreds of
eV or so, but gamma radiation can have energy maybe
up to KVs,
maybe MeVs, maybe several tens of MeVs also.
Even in KVs, these are called harder X-rays, which are coming from not necessarily from the neutrons, the auger electrons, the inertial transitional inertial electrons also lead to the softer gamma rays. Nevertheless, it was a very useful and very interesting session, Professor Singh. We enjoyed. We are now running. I have many questions. Viewers, thank you very much for your interest in showing your interest and asking questions to us in this. We will be able to take up all other questions maybe in a subsequent session after some time. So thank you very much once again, and we are back, coming back for the 37th session on 22nd of July 2022, when we are going to have Dr. Avnish Kumar Srivastava from CSIR AMPRI Bhopal laboratory. He will be speaking about self-reliant India, a materials perspective, where he will be talking to us about the microscopical systems and the materials testing mechanisms, STM, SEM, etc. So it will be another interesting session, and Professor Dr. Srivastava will again be with us in our studios. So thank you very much till then, and have a good time. Bye. Namaskar.